Okay, I think I've started the recording. So is there a way to double check? Okay, yeah, it's on. All right, folks. So today we are starting with the two-phase locking, right? So even before we get into two-phase locking, just a quick recap of the different isolation levels that we saw, and like maybe like a pop quiz kind of stuff, just to recap, at a very basic level, right? So let me pose the first question. So basically, we had, we started with weak isolation levels in this chapter, and we realized that, without any specific steps to prevent the inconsistencies, there'll be like two main issues that we would see. One is called dirty reads, the other one is called dirty writes, right? So what is the first weakest isolation level that would actually solve dirty reads and dirty writes that we saw?
Read committed.
Perfect, right? So we saw read committed, and the way read committed does is it actually locks in order to prevent the dirty writes. It uses locks, row level locks, and then it maintains a couple of versions, one for committed and one for uncommitted writes, so that like the reads are always coming from the committed version, right? So okay, so that's one. And so the book then talks about the problem that still exists even after we implement read committed, right? So which is actually a read skew or a non-repeatable read. And what is the next isolation level which would help us to prevent um, the read skew problem? So read skew is happening because as my transaction is executing, like T2 has committed something, right? And the effect of that commit is being visible. So the solution that is proposed is, you could use snapshot isolation, like where when a transaction starts, it kind of takes a snapshot of the current state before it starts, and then it only looks at the snapshot, right? So everything is frozen for the current executing transaction, right? So we saw that, and we also saw that the main theme behind snapshot isolation is readers don't block the writers and writers don't block readers, right? So this would really enable long running transactions, that does a lot of reads and that actually doesn't do any of the writes, right? So they don't actually have to wait or they don't have to abort. Right. So, and the way snapshot isolation is implemented, if you guys remember, is using multiple versions, right? Like, so whenever a transaction starts, there is a new transaction ID, and it actually remembers the transaction IDs of the current snapshot that were all committed, right? Of all the transactions that were committed. And so then in addition, so all this, even snapshot isolation solves the problems with respect to the non-repeatable reads, right? So we also saw a couple of more issues with respect to writes. I think the first one is called lost writes, right? So where the writes get lost. Like the best example to understand lost writes is, when you have counters, right? So you do a read, modify, write cycle, right? So that's when you actually have lost writes. And we saw four different methods the book kind of tries to explain: atomic writes, compare and set operations, explicit locking, and then automatic detection of lost updates. Right. So, and it appears that most databases support automatic detection of lost updates. So based on which, we don't have to worry about lost writes from the application level. Right. So that's one thing. So the next write related issue that we saw was write skews, which has to do with phantom writes. And we saw that the phantom writes usually follow a specific pattern. There is always a select query, and then there is a predicate condition that gets checked, and then there is an update that happens. And when two transactions execute the same set, and if the update actually kind of modifies the result of the predicate condition, so then we result in this phantom writes or write skew, right? So, and so the solution that we saw for write skew was, if we can log the select query, right? So if we can kind of issue a lock on the rows that would fit in the select query, so then the update can actually be blocked, right? Like, so, like if we already figure out the way that there is already a lock on the select query, right? So that's the solution. And so all these are weak isolation levels, right? So, and then, so the next thing that we started seeing was serialization. And I think last week we saw actual serial execution, right? So which simply means, implement what the what serialization actually means, right? Like, so execute everything serialized in a serialized fashion, right? Which would solve the problem, but it's just the fact that you don't have any parallelism over there, right? So, and then, um, so for today, we are actually going to see two-phase locks. And so the best analogy to actually consider what two-phase locks are, I think most of us, when doing concurrent programming, right? So we would have definitely seen read-write locks, and two-phase locks are almost exactly the same. And it looks like this was the most widely used method to prevent to actually implement a serializable level isolation, serializable isolation level, right? So, and the two-phase locking, as the name implies, there are there are two different kinds of locks even involved, right? So one is the shared lock, which is analogous to the read lock and a read-write lock. The other one is an exclusive lock, which is analogous to the write lock in the RW lock that we have seen, right? So so the idea is, whenever if let's say a transaction wants to read a specific object, right? So, and so the read lock is like allowed. The shade, it has to obtain the shared lock in order to read, right? And so when can it obtain the shared lock, right? So as long as there are no exclusive locks on that particular object, the shared lock will actually be given to the transaction, right? Even if there is another transaction that has already acquired that shared lock, right? So because it's a shared lock, any other transaction that wants to read the data can actually acquire the shared locks, right? So the only condition that's going to prevent from acquiring a shared lock is there are no mutual locks, so there are no exclusive locks on that particular object. So this is the way to actually get a read level lock, or what we call as a shared lock over here, right? So then what is the condition to actually get a write lock, right? So the condition to get a write lock is, let's say I want a write lock on a specific object. The object should not have any locks associated with it, either being shared locks or the exclusive lock, right? So only if that object is completely unlocked, so then I can go and get a write lock on the object, right? So here, if you guys actually remember, the theme for a snapshot isolation is readers don't block writers and writers don't block readers, right? So that's the reason why snapshot isolation performance is high, and it permits those long running read transactions, right? But in this specific case, if you guys look at it, like if there are readers like that have acquired that shared lock on an object, then writers actually are blocked, right? So similarly, I mean, if there are writers that have acquired an exclusive lock, then both readers and writers are blocked, right? So which means the theme for two-phase locking is readers do block writers and writers do block readers, right? So that's the nature of like how a two-phase locking works. And I think that is also the reason, kind of why the two-phase locking's performance is kind of bad, because I mean, if at all there is any possibility of a race condition, like between two transactions, then they would actually have to wait because of the way in which they are going to acquire the locks, right? So I mean, as long as there are two transactions that are completely looking at different like a different set of rows, I don't think they would be blocking each other, right? But if they want to operate on a similar set of objects, right? So then, like if they had acquired a read lock or a write lock, so they would actually be blocking other writers, right? Or if they acquired a write lock, they would block other readers and writers as well, right? So that's why I think the main issue that the book kind of talks about with respect to the two-phase locking is to do with the performance, right? So it kind of at least like for those transactions that kind of have that might result in race conditions, they are being executed in a serial kind of fashion, or they basically have to wait for the locks to become available. All right. So, and the book also goes on to talk about one another factor that comes into picture over here. Why two-phase locking is a little bit not heavily used, at least like in the recent days, is because the latencies are not predictable anymore. right? So depending upon the contention that's in of the current scenario, like, and depending upon the number of outstanding transactions and what parts of the region they're executing on, like, these latencies are really, really unpredictable, right? Like, they could be extremely high or low, depending on how the situation is, right? So that's one of the reasons, like, when you have unstable latencies, then it's a problem with the application has a problem, right? So you need predictability, like, when you're issuing your transactions and stuff.
So,
Yeah,
sorry to interrupt.
sure.
Can we specify one use case scenario that appropriately fits in the two-phase locking? Like one example, one sort of scenario where two-phase locking would be the best solution.
So, like, whenever we want a complete serializability, right? Like, let's say you have, if the so two-phase locking is a way of implementing serializable transactions, right? So
Yeah.
if your isolation level is set to serializable, meaning that you want the effects of two different transactions uh, as though they executed one after the other, right? If that is what you
Okay.
desire, right? Let's say, for example, you don't uh, 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 let's say you have transaction T1 that's actually that's kind of reading and writing to, let's say, a couple of objects, A1 and A and B, right? So, and you also have simultaneously you have transaction T2, right? So that actually works on the same region as transaction T1, right? It's also trying to read and write from A and B. But what is the effect that you desire, right? If your transaction isolation level is set to serializability, like, the way you want the outcome after both T1 and T2 have executed is such that you would want to have executed T1 first and then T2 later, right? So in serial order, right? Or T2 first and then T1 later, right? If that is the outcome that you desire, right? So which means that you don't want any of the previous anomalies that we saw. You don't want dirty reads to happen. You don't want dirty writes to happen. In addition, you don't want read skew. You don't want lost writes. You don't want any kind of write skews or phantoms. So then the only way to prevent that is making sure that these two execute in a serialized fashion, and two-phase locking would be the best way to, at least, like, as of now, the what we have seen so far, two-phase locking is the best way to implement that.
Okay. Yeah. Thank you.
Yeah, it has to do with, like, what kind of isolation level that I desire. And when I say that I want this particular isolation level, in this case, when I set it to serializable, which means you don't want any of the anomalies that we have seen so far,
Okay.
right?
Yeah.
Like, the
Okay.
the 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 isolation level that we saw before serializability, the last isolation level that we saw was snapshot isolation, right? But we saw that snapshot isolation still has problems with respect to lost writes and then write skews, right? So how do we avoid all these anomalies? Then we go for serializable transactions or
Okay.
serializable isolation level,
Okay.
right? I mean, the example that I gave is not a very specific application
Yeah.
level
Yeah. But
example,
it's the
but
idea actually that
yeah,
we are implementing and not a specific example actually.
okay.
Yeah.
Anyone else wants to add a little bit more that would elucidate the concept in a better way to Rabani's question?
In the references, there is an article actually.
Okay.
So a redditor actually mentioned that he was able to steal 100 bitcoins from a popular Bitcoin exchange, and the Bitcoin exchange was using snapshot isolation itself. So
Okay.
the user was actually trying to do hundreds of 0.001 transactions and one big transactions at the same moment, and it happened that that 100 bitcoin was lost due to snapshot isolation.
Oh, I see. Okay, so okay, so the 101. Okay, so that became a lost update problem, is it? I see.
Yeah.
Yeah.
So in that he mentioned that they took a lock on at the account level, and I mean, he didn't mention that they implemented, I mean, they used it serializable or not, but
Mhm.
they said that they required a lock at the account level, saying that only one transaction could happen at the account level, and still use it snapshot isolation itself. something like that.
I see, I see, I see. Okay, okay. So yeah, if all we want to prevent on top of snapshot isolation is lost rights, then explicit locking kind of solves that problem, right?
Okay.
So, but there is, yeah, so I think most databases, it is kind of mentioned that most databases kind of support detection of lost updates, right? So probably the database that they were using like doesn't support that, and that's the reason why the transaction was not about it, I believe.
No, no, no. Actually, most of the uh, databases come with the default. I mean, even Oracle, the other mentioned that the highest isolation offered is snapshot isolation itself.
Okay, so they don't, so you're saying that they don't support the automatic detection of lost
Yes,
updates.
sometimes. I mean, some of
Okay,
the databases still don't support it.
okay, I see. Okay. Nice, nice. So that's a actually that's a cool example of when to definitely, especially yes, of course, right. So when you're
When
dealing
not
with
to
money,
use.
when you're dealing with money, yes, it becomes really yeah. I think the default level, I think that's where people kind of miss it out. I guess I think so. For Oracle, the default isolation level is still is it read committed or snapshot isolation? Any of you guys remember for Oracle or MySQL?
They actually, I mean, not sure about Oracle, I mean, MySQL, but Oracle, the serializable itself is snapshot isolation. That's
Oh,
what the
okay.
author does.
I see. I see. Okay. Marketing. Okay. I see. Nice. So okay, so let's okay, so we just saw the two-phase locking, right? So and so so I think to make the two-phase locking as a complete implementation of serializable isolation level, we still have to support predicate locks, right? So predicate locks is nothing but if you guys remember the concept of phantom writes that happen, right? So there's a specific step to we saw this example of Alice and Bob, right? So there is always this three-step process that happens in these kind of patterns, right? So you do a select query, and then based on that you check for a specific predicate condition, and then based on that you actually do an update, right? And two transactions can simultaneously do this, and what happens when they simultaneously try to do this is like if the update actually changes the predicate, right? Like or the result of the predicate, right? So when they simultaneously execute together, when if Alice executes first, right, and then her update changed the result of the predicate, but the predicate was already checked by Bob, right? So then whatever update that he's going to make is actually going to be inconsistent, right? So because the predicate is not valid anymore. Right, so that's the theme, and I think we kind of already saw this a little bit before as to how do we prevent this specific anomaly, right? So if you can get a lock on the select query itself, right? Like, so we kind of saw, I think in the last session, if the lock can be applied to the rows or basically to the can be attached to the condition of the select query itself, right? So then, when the second transaction tries to execute, it would actually be not able to do the update, or it would not be able to even do the select depending upon what the timing is, right? So we can actually take a look at how it happens, right? So and the predicate locks idea is you take a shared lock on the select query. All right. So you take a shared lock on the select query and you take an exclusive lock on the update query. Right. And we can actually see how that plays out in Alice and Bob for different scenarios. Right. So let's say Alice comes and she executes a select query first. Right. So which means there is a shared lock on all the rows, like that satisfy that on call true and shift ID equal to 1, 2, 3, 4. Right. So we have that shared lock acquired. Right. And then what could happen after? So let's say Alice goes on to execute the update even before Bob comes into picture. So in that case, actually, we are fine because when Bob comes and executes the select query, he will be able to see the result of the update and he's actually okay. I think the problem happens when Bob comes and tries to execute the select query before Alice does the update. You guys can see that, right? So now let's say Bob comes and executes the select query. Bob would still, because it's a shared lock, Bob should still be able to acquire the shared lock, right? The predicate lock, right? So all fine, right? So now when the Alice tries to execute the update condition, right? So I think that is the point where the update condition will not actually proceed, because it will see that the predicate lock will basically tell the fact that, there is a select query that has already acquired the predicate lock, which means it's actually done the read, and which means like don't grant this specific update exclusive lock for this particular update, right? So this update query by Alice she wouldn't be able to execute that update query until Bob actually releases his shared lock that he acquired on the select query, right? So which means that, when someone executes a select, they kind of put a shade lock over there, right? And if anyone is kind of trying to change the results of the select query using an update in their own transaction, they will not be able to do that, because of the fact that the predicate lock kind of tells them that there has been a select that is actually on there has been a read on these rows that you're trying to modify. So the whole problem, as you guys remember, the phantom happens because you're modifying the result of the read, right? So if you block any modifications on the results of the read, that is exactly what the predicate lock does. But there is one thing that actually, if you guys remember and look at this example closely, right? So I was actually able to figure out a deadlock, when I applied it in one ordering, I could see, but the book kind of mentions that, right? So the moment two-phase locking comes into picture, the book kind of mentions that there's a lot of scenarios where deadlocks would be there, right? Like, so, and I was able to see one specific condition over here where we actually got a deadlock, right? So, can you guys
And
see that?
yeah, so because Bob has also taken the reader lock on those rows, so Alice will not be able to modify it. Like Alice will be waiting to modify those rows, and Bob can also not move forward because Bob wants to make uh, that row false. So because that Alice and Bob rows are selected by both of them, and both of them have reader locks,
Hmm.
so they won't be able to move forward, right?
Exactly. Exactly. Yes. So exactly. Yeah. I think that's one
Y-
correct.
Yeah, but like I was thinking, so how do these databases avoid deadlock? Like, what is the resolution? What would they do?
I think I think they would have internal deadlock prevention. So these are actually not even prevention, right? So probably they'll have a deadlock avoidance algorithm, or they'll be able to figure out deadlocks, right? So usually, if you guys remember, so let me try to think. So deadlocks happen if there are a certain set of conditions that are present, right? So I think in OS, it's based on, hold. There are certain conditions called hold and wait, circular wait, no mutual exclusion, right? Like, so no preemption, right? So those are kind of four conditions to actually hold in order to actually have a deadlock, right? So I think like when the databases will actually be able to see that, like T1 is blocked on something which is held by T2, and it will also see that T2 is blocked on something which is held by T1, right? So this is one of the conditions of deadlock, and they call it a circular wait, right? So the databases should
Yeah.
be able to, the transaction manager should definitely be able to see these circular wait conditions, and I think it should be able to prevent it. If it doesn't, then the transaction has to time out. That's the only other way in which this would work, right? And then the next execution doesn't happen in the exact same race condition scenario, and then it'll again, right? So hopefully, I think uh, um, the deadlock detection algorithm, which would be able to see the circular wait that happened over here, right? T1 holds something and T1 waits for something. T2 holds something and T2 waits for something. And whatever they're waiting for is being held by T1 and T2 mutually, right? So that's the reason why we have the deadlock over here. I definitely either the database should be able to see these conditions and abort, uh, or the other thing is that we have to wait for the timeout, right? So that's the I mean, where there is, if there is no deadlock prevention, or I think so. If you guys remember, like the rules, so some of the design philosophies to actually prevent deadlocks, right? Is make sure to acquire the locks in a specific order. or something, right? So each transaction will always acquire the locks in a specific order. There are a few different philosophies to follow to even not get into the state of deadlocks, right? Because deadlocks usually happens with respect to locking scenarios, right? Um, I believe so. Here I'm not able to see what kind of strategy the application should follow directly to prevent the deadlock, right? Because usually if the locks are acquired in a, usually the reason why it happens is because like T1 was able to acquire L1, right, and then T2 was able to acquire L2, right? And then T1 is now trying to acquire L2, and T1 is now trying to acquire L1, right? So they are acquiring the locks in different orders, because of which deadlock happens. So one of the deadlock avoidance strategies is to always make sure that the locks are held in the same order. So in which case, T1 would have acquired L1, T2 will not go on to acquire L2. T2 also will try to acquire L1 first before it tries to acquire L2, right? So in which case, T1, it doesn't happen at deadlock. T1 will not even be able to acquire L1, right? So that's one of the deadlock avoidance strategy that's usually followed. Acquire the locks in a specific order, right? So I don't think here it applies because it's a shared lock. They probably both would be able to acquire that. So, but the book specifically mentions that when you have two-phase locking, you're prone to many deadlock scenarios, especially if there's a lot of contention around similar objects and stuff. So I think it's probably not a very uncommon scenario to happen. Does that give a little bit of idea? So I know I couldn't answer the question exactly how a database would prevent it, but I think in this case, at least, the circular wait scenario should be detectable by the database.
Yeah, no, makes sense. Yeah. Yeah, no, even I could also think of just like aborting after a timeout. Yeah, I could not apply any of those strategies to avoid deadlock here. So, yeah.
Cool. Okay, so we have um, okay, so we were looking at the predicate locks, right? I think the predicate locks is just a concept as to how to prevent this, like this three-phase process of select and then predicate and then update based on the predicate, right? So the book actually talks about the fact that the predicate locks are kind of time consuming, uh, um, uh, or it's basically an expensive operation, mainly because of the fact that you have to check for, like for that particular, when that particular update executes, right, it has to actually check for, like, okay, the update is executing on a specific row, so it has to check for all the shared logs that might exist on that particular row, right? Like, and that kind of becomes a bit expensive, so especially if there are multiple active transactions and stuff. And they say that, the better way to implement an actual predicate lock is if you can directly do it on an index, right? Like, so, but like, and they gave the meeting room example for the specific scenario, saying that, hey, in the meeting room, even though we are trying to book for a specific meeting room as 1, 2, 3, 4, and then we are also trying to use a specific time slot, say 12 p.m. to 1 p.m. Like, if we can actually put a log on the index, right? So in this case, either the index on the room ID or the index on the time slot, right? But the problem with that is, if I put a log on the index on room ID 1, 2, 3, 4, it's going to block it's going to block the room for that entire day. Right. So you're kind of putting, so even though you're only required to block, like for a specific set of time IDs where you want to kind of check, but you're actually kind of blocking the whole thing. But in terms of lock on the resources used, it's a direct lock on the index, right? So which means that the number of locks that you would have to check, when someone tries to try to update, is just based on that one index lock over there. Right? Instead of multiple, let's say it's based on multiple rows, instead of doing it on having multiple of those predicate locks, now there is only one index lock, right? So and even if another transaction kind of like tries to log these some of these rows, it will probably be a subset of these index locks, in which case we don't actually have to maintain it as a separate index lock, right? So I think the idea is to kind of expand the locking scope right? Like, so instead of having very specific individual logs, you try to expand it to an actual index, right, or a set of rows. And even though that scope is actually more than what is necessary, they say it kind of simplifies the actual execution process of checking. Like when an update tries to execute, right, the check is just having to have a look at the index and see, like if there are any if there are any other if there are any index range logs that actually satisfies that particular index or not. Do you guys get this, right? It's a little bit like there's a very small portion of what they're saying as to how it how it kind of like helps to reduce the number of checks, right? The only way I could kind of materialize it in my head and coherently apply it over here is, like the individual. So when you have individual logs, right, like, so which is the individual predicate logs, it might span over multiple rows, and for each row you would actually have to maintain one lock, right? Let's say if you would have to end up locking 10, if your select query ends up locking 10 different rows, right, or 100 rows, for example, right? If you don't actually have an index lock, right, then you would be creating 100 individual predicate logs on those 100 rows of the select query, right? And now, when the update actually executes, right, that update individually has to check for all the conditions of whatever the update field is, right? So in this case, like, it's probably even more than those 100 rows, right, like, to see whether there are any predicate logs that are being held, in which case I should not proceed, right? But instead of those, like, 100 different logs, like, if I simply have on lock on the index, right, the index simply specifies the range where the lock is held, and then, on my update I can see whether my update falls in the range or not. So it's a single check, right? Like, so that's the way I was able to materialize it in my head. If you guys have a better way of explaining it, please chime in.
So, while update, why would we have to check all the logs in the predicate logging? Won't we need to just check whatever row we are updating, is it already logged or not?
So, okay, so when I do an update, right, so I'm specifically trying to do an update on a specific row. Oh, yeah. So I think the reason is because, let's say I'm trying to, if I'm trying to update for a specific room, let's say 1, 2, 3, 4, and for a specific time slot, say 12 p.m. to 1 p.m., right? Um, is it enough to only check on, because I would have to check on the row that matches.
So, yeah,
Uh,
I'm talking about like the previous example of predicate locks. Like, let's
right.
take an example of this Bob and Alice, right? So
Yep.
we will be taking lock on Alice, read lock. We will be taking read lock on Bob. And now when we have to update, like, let's say for Alice, so we will see whether the Alice row is already logged or not. So we can just check Alice, right? Because we need to update Alice, and that will already be logged.
Right, right. So, but the so is it, so the update condition, would it only match a specific row, right? So,
Which it wants to update. Yeah, I was thinking, yeah, that it does not need to check all of them, just the one which it is
because
waiting.
it's specifically looking for Alice, and then shift ID equal to 1, 2, 3, 4, which corresponds to a single row. I see. I see.
Mm.
Okay. Okay, so yeah, so in which case it doesn't actually have to check, it only has to check whether, it doesn't actually have to check on all the rows that match the select query, but it only has to check on the specific row that I am trying to modify.
Yeah, but okay, yeah, yeah. In this case, it's fine, but I don't know if there are other
Other
situations
cases where we have
where
to
we
check
need to check. Yeah, yeah,
for all
mhm,
the rows held, right? So,
yeah, yeah.
yeah.
Does it say in the book that it needs to check for the all the rows? Then probably there might be some other situations. Cannot think of right now.
So
Okay.
let's say the predicate for Alice was like 15 to 20 rows, right? So that
Mhm.
update condition would check the log only on the 15 to 20 rows, right? And that's what you're saying.
I think Abhishek is kind of mentioning that it doesn't even have to check for those 15 to 20 rows. The update condition just has to check that one row that it wants to update.
Okay. Okay.
Right, like, so because I was under the assumption that it had to check for all the 15 20 rows, right? And that is why I was able to kind of understand how the index range kind of saves the time, instead of having to check for like for all those 15 or 20 different logs. You can simply look at the index and find the range and see whether my update is inside the range or outside the range, right? but
Yeah.
uh, but Abhishek kind of is saying that we may
That
not,
that makes sense actually.
right, so we only have to check that one row. So,
Might, might be needed, right? Because
mhm,
let's say if let's say we are actually, you actually got the current on-call count as two, right?
right.
But that may not be valid if someone is actually adding another doctor to on-call shift or something, right? So you need to hold the whole. Since uh, you are doing a count star from doctor, on call equal to true. So you need to have a lock on all the rows that this query is touching, right? Because the current and after the select you are doing a current on call equal to 2. uh, if someone is actually adding another doctor to the on call,
Mhm.
this the second would have been uh, wrong, and that wouldn't be actually serializable, right?
I see. I see. Okay. So, so you're talking about those phantom insert rights, right? So where
Yeah, phantom.
somebody's, yeah. So okay, yeah, I think, that is one way I can definitely like see why it has to be on the index rather than on the exact, because when I try to do this simply using predicate logs, right? So I cannot actually log those rows that don't exist as of now, right? So in that case, like if I don't actually hold an index log, so then how would I even like how would I be able to figure out that this new write is actually it actually affects the condition of the select,
Yeah.
right?
Yeah.
Yeah, thanks. Yeah, I think that makes perfect sense to have. The book doesn't explain it that way, but the reasoning as to why we might actually have to put it on the index is we are trying to not only put the logs on the rows that exist, but we are trying to, because the select query can actually span over all possible rows that do not exist, but that might get inserted as part of another transaction, right? Yeah, that's perfect.
So, yeah, I understood this situation. So, how will the index help? Because, like, I'm like, exactly how does it work? Because that new row which has to be inserted, the new doctor which has to be inserted,
Mhm.
uh, how would we know it's indexed before, and like, how would we already apply lock through
Right.
index range?
Yeah, so so if you look at for this particular specific example, right? So the so on what index on this example we would actually have the lock, right? So we would simply say that select count star from doctors, right? So where on call equal to true, right? So maybe we would actually have uh, um, uh, we would yeah, so exactly, so it's based on the count, right? So yeah, we would have actually maybe set on the index where like the for the index where the on call equal to true, and that new insert would actually change that specific query condition, right? So when I do a new insert of a doctor, like with on call equal to true, for example, right, that basically changes the count value, right? But because I am inserting it with on call equal to true, so that actually fits in with the index that I've actually maintained, which is actually on the condition where like on call equal to true. Isn't that the case? It's more evident if you look at it on the reservation book, on the reservation room example, right? Like, so like I'm right now checking to see whether there is a reservation for room 1234, right? And then let's say there are no reservations, right? But I'm holding a lock for room 1234. And if someone tries to even though right now there are no rows, right, but when someone tries to kind of insert it, like on that 1234, right, like they're trying to book 1234, right? If if I have an index lock on 1234, right? So then that particular entry will actually pass that index check, right? So which means that like we know that currently there is a lock being held for that, which means like I will not allow the update.
So, yeah, so exactly what do we mean by index lock here? So there is this room 1234, and if we take a lock on that 123, the row of the room,
So all
uh,
the yes, so on an index on that particular column, we are taking a log on that entire range that spans that particular value 1234. That's the meaning of that index log, right? So
so
it's for that index is on the column called room ID, right?
okay,
So
okay.
and there are like let's say there are 20 different slots, which means like there'll be 20 entries for room ID or whatever, right?
Mhm, mhm.
Right, maybe there are just three room IDs that were booked, so there'll be like the index lock actually is held for those three IDs. And not only that, even if someone holds the index lock on that for room 1234, let someone is trying to insert like an entry for room 1234, right? So the index check is that like, hey, is there a lock for that entry 1234? That's the index check, right?
Mhm.
Right, so in which case it actually kind of that it passes the check, right? So which means that we know that, okay, there is a lock on this particular, I'm trying to update something, but there is actually a read lock that is being index lock that is being held over there, which means I shouldn't be able to update. And it need not be, the index thing is need not be on specifically 1234, right? You can actually specify a range, right? You want to log all rooms that start with 100 and end with 300, between 100 and 300, right? So because you have an index on that column, it is not just spread over one specific value, it could be spread over multiple values, right? So now you're kind of blocking, when you have all that lock, right, you're kind of blocking anyone trying to do an update, like on those, on any of those 100, 200, and 300 numbered rooms,
Okay, yeah. Mhm.
right?
I,
So
I can think of one more scenario where probably index range locks may be helpful.
mhm.
Say we are designing a concurrent LRU cache,
Okay.
and um, I mean, when I say concurrent, so probably multiple clients are trying to change a value. Um, so either we can go for a coarse grained locking or a fine grained locking. With a fine grained locking, probably we'll have a lot of locks depending on the size of the cache. But probably index range locks, as I understand, would fit somewhere in between where they can hold a range of objects. Um,
What is the difference between coarse grain and fine grain locked? I
Yeah.
so
haven't
fine
read.
grained, I understand, is for each of the key we will have a separate lock. Coarse grained is something like for the full cache you will have only one lock.
Or for an entire range instead of a full cache, maybe for a range.
Yes, and this looks to be somewhere in between, as you were also mentioning, right? For a 100 to 300 room, we can have one lock, and probably for 300 to 500, we can have another lock. Something like if I know the range of values in the LRU cache or any cache, then probably I can use this kind of lock.
I
Um,
see. Okay. Yeah. Similar scenario, I guess, right? So yeah, the
So
idea is, yeah.
and so this index range locking kind of thing, I think application would have to do it, right? Database would not know what index it should appropriately take lock on.
I believe so. I think
And
when it issues a select query, right, it will probably issue it on the select query. It will explicitly say, I think there is a select for update, I guess. There's a statement, right? So the application explicitly tells that, like it needs the condition of the select to be locked. Yes.
so I mean, yeah, I was thinking then it can
Sure.
create problems because the application has to make the right decisions that this index range will be helpful in avoiding like any of the like any of the wrong updates to the data, and like those assumptions have to like be carefully thought through by the application, right? That what index it needs to actually take log on, like if the application has decided that the index is room between 100 to 200. So yeah, I mean that assumption, how to validate that assumption, like application should know it. The application developer should be careful about it.
I guess so. So I'm not sure whether the database would be able to see, let's say let's say we specify serializable isolation level, right? So and then we simply without using a select for update, we simply give the select query like how this Alice and Bob example gives that, right? So if we simply do that, so then like yeah, either we explicitly kind of specify in the application using a select for update, or the database might should be able to see that scenario, right? Like so when it looks at the set of queries in the transaction and sees that like there is an update that's kind of trying to modify the conditions of the select query. I'm not sure if if it is something that databases internally implement within their like to check and see whether having to have because I don't think a database will always issue this range locks for all select queries, right? So one simple way to kind of always enforce it is whenever you see a select query, you always take an index range lock on the select query, right? Because hoping, not hoping, guarding against the fact that if at all the user has an update, I mean, a predicate after this, and then an update based on the predicate, then we would be like, like we would make sure that like nothing wrong happens, right? So I
So
think that's.
let me add one thing here.
Mhm.
There are locking, right? There are multiple aspects of it. Here,
Yeah.
whether your application level locking or database level locking, or and even the locking for the database, it depends from whether you're using SQL Server, Microsoft SQL Server, or Oracle. Though they are almost similar, but there are subtle differences. So when you want to, you cannot generalize all lockings will work exactly. So memsql will work differently from Snowflake will work differently. So the final or MapReduce or Hadoop database or so you have to be subtle. You can give general statements,
Mhm.
but when you're actually implementing this, the lock escalations from row level to table level, how the escalation happens depends from Oracle to SQL Server. So you have to be a little bit careful about when you're in an interview or something. You can say in general this is how it will work, but we have to take into account how that end database is, what is whether, and also whether you're updating via a stored procedure versus updating via an API, updating via. So there are multiple aspects to it. How you want to update it. So you have to
Okay.
take that into account. Yeah.
Okay, sure. Yeah. 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 I think even the book kind of supports your theory, right? So they kind of talk about the fact that whatever they even mean when they say serializable, like I think even someone mentioned before, right? When they mean serializable, they are literally just doing snapshot isolation, right? So
So
I
when you
think.
do a database, right? Database, like if you are using SQL Server, you have select star with no lock, with lock isolation. So yeah, there are different hints that you can add to a query to see whether you want to give a dirty read, like where shift ID is equal to 124 or Alice, right? Whether the Alice is completely committed or it is still in the cache or it is dirty reads, right? So if you are in a transaction begin and try catch blah when you're updating. So if you say dirty reads, then even before you commit the row level, you can still read the data. If you say ignore, I don't care if it's committed or not, just give me what's the current value. In those scenarios, customer has that. If you're not worried about how the data may look like, you just want to know if the data is there or not. So in that scenarios, if exists, you don't care if shift ID is name or not. But if it's not a bank or something, when you want to withdraw, then you have to do more checks. But initial check, you can just do the dirty reads and get away with it
I
without
see. So
blocking the row for a longer time.
okay, so usually, yeah, so I understand that for every transaction, you can set what the isolation level could be, right? It's not just at a generic level. So for
Yes,
each transaction, you can set. But what you're saying is even further, for like different statements within a transaction, you can set isolation levels, is it?
exactly. Yes.
Okay, I see. I see.
But you have to be
Yes.
very careful. You should not, unless you know the behavior really well,
Uh-huh.
you trust the database. But if you see locking and this thing, and when you do performance optimization, only then you need to add hints and locks.
I
Because
see.
if you add hints and locks, if a new update comes and the database fixes it, then your hints may be counterproductive to what that latest version of update sees. So if you see production issues, or if you see this may be an issue based on the current behavior of the database or your API, or how you're calling the updates to database, or multiple APIs from load balancers or something, how it's coming, based on your application you have to deal. But ideally it's not good to add hints or
Mhm.
explicit logs, unless you know your application really well.
I see.
What is hints?
Hints is basically update whether you want row level locking. Sometimes database does row level versus table level escalation, right? If it sees lots of table level locking is happening, row level locking is happening, then automatically it will escalate to table level locking. And that is like and hints is basically with no lock or something. Select star from AB, select star from doctors, where with no lock or something like that. You can search for locks, lock escalations and hints. Every database SQL Server has different from Oracle, so you have to look into that versus MySQL.
I see. Okay. Thanks. I think yeah, that kind of clears up, right? So we have to be always cautious as to what each database supports and how it even implements when they say they support something.
Yep.
Amazing. Okay. Okay, so fine. Yeah, the last one, right? So far we saw the two-phase comments, right? So we started with the two-phase comment, and then we kind of branched on to how to even with the two-phase comment, we still need the support for these range locks, right? Index range locks, which is nothing but the predicate locks, right? So the next which is basically the last way of implementing. So the what we saw was the second way, right? So the three different ways. One is like like actual serial execution that we saw. The next one we saw was the two-phase locks. The third one is the serializable snapshot isolations, right? So so I think the basis of this SSI is, I think if we are familiar with how we write concurrent programs, I think we should be able to grasp this fast, right? So like whenever we try to access a shared object or a shared memory. So what we try to do is like either you can use explicit locks, which is actually mutexes, right? You use mutexes, you basically protect the region, your critical section, and then you make sure that nobody accesses it, and then you finish your work, and then you can actually release the mutex. Right? So that's one way of doing it. So the other way, that's basically the pessimistic concurrency control, right? So where you use locks explicitly. So the other way is what they call this as optimistic concurrency control. So in optimistic concurrency control, what you do is like, so in locking, we kind of prevent the other transactions from executing, right? Because they also need the lock and they can't execute unless the first one finishes off. So in the optimistic way, so the way you do it is like you allow the transactions to simultaneously execute, right? Hoping that there are no like contentious rights, right? And if that's the case, you're perfectly fine, you have not acquired the lock and everything is okay, right? Like so, and both transactions can execute perfectly, right? But if there are contentions, then one of the transactions has to abort, or maybe only one transaction would succeed, right? So that's the idea between like pessimistic versus optimistic concurrency control. A simple example would be like in our concurrency programming, we have this cache operations, right? Compare and set operation. So where you don't actually acquire the lock, but like, so you issue the compare and set operation, you read a value, and then you do an increment on the value or whatever you want to update it to, right? And then you do a compare and set, like giving the old value, saying that, what, hey, if no one has changed in between the time that I read this and updated this, and I'm right now trying to update it again, right? Like, so issuing the command, if no one has actually, because the old value that I saw, right, my causal dependency is the old value, right? So you specify what your causal dependency is, right? And then your internal system or your internal OS or your so it would be able to actually figure out, whether there is a violation or not, right? Whether there's a conflict or not. If that's the case, it'll actually abort the operation, and then your cache operation will not succeed, right? So then you'll have to reread the variable again, and then you'll have to update it again, and then try to issue the cache, right? So this is the optimistic way. So okay, so what's the point, right? Because like every time I try to do that, somebody has updated it, so then I have to retry it and again. The thing is, under situations where the contention is less, this would actually be a huge success, right? You don't have to, because if let's say I'm the only thread is going to execute, right? So, and then every time I log and then I do something and then I unlock, like it doesn't make sense, right? So in those cases, I probably don't want to, right? But there are scenarios where the contention might happen, but as long as it's limited, we are okay, right? I think the best example is, like if you have thousand, I'm just as an example, right? If you have thousand threads that are looking at a value, let's say X, right? And then X is now 1, right? All the 1,000 threads are using concurrency operations, right? So what is going to happen is all the 1,000 threads are simultaneously going to read X equal to 1. They're going to update X to 2. They're going to issue the cache operation saying, hey, update X to 2 if the old value is 1. And what's going to happen to these 1,000 threads? Only the very first one that executes, that finishes the execution is going to succeed, right? All the other 999 ones will actually fail, because they say if the old value is 1, right? But when the first thread executed, it would have changed the current value from 1 to 2, right? But all these cache operations say that, hey, like do this update, giving the value that I saw, which was actually 1, but the value that is there is not 1 anymore. So all these 999s will actually fail, right? So out of these 100, so that is why, you have to be careful as to under what, if there is really a lot of contention, it's even better to use logs rather than using optimistic concurrency control. So we have to be a little bit careful on that. And um, and yeah, so I think the main idea of serializable snapshot isolation is this, right? So which is like using this technique of optimistic concurrency control, right? Like, and using snapshot isolation alone, right? I allow the two transactions to proceed using snapshot isolation, right? That's what I'm trying to do. And if at the end of it, when a transaction tries to commit, right? If I see whether the serializability has been violated or not, all right. So if it has not been violated, perfect, right? So then I can actually go ahead and comment, right? But if I see that, like if one of the other concurrently executing transactions has committed something that's going to violate my the serializability thing, right? Where you're going to give the result as though they executed in serial order, right? If it kind of violates it, so then I have to abort it, right? So how do we even figure out? I think that's the last couple of things that we have to discuss before we close off for today, right? So how do we even figure out, like the serializability has been violated, right? So the book actually talks about like two different, yeah.
Johnny, so sorry, some interruption. So,
Yeah.
so basically, so one important point here that book mentioned is that, uh, so optimistic versus pessimistic, it's not always, we can say that optimistic locking is better, right? Because if there is lot of contention, if you are failing again and again with optimistic, if you have to retry,
Yeah.
then optimistic locking is not a good approach. So, and basically they are talking about this serializable snapshot isolation, because they said that uh, the approaches which we have discussed for serializability, they are not good at performing, right?
Yes.
And serializable snapshot isolation is something which will give you serializability as well, and it will also help you do good performance. But again, if it is doing something like optimistic, where you are first taking the snapshot and then checking whether your data was actually modified or not, isn't it similar problem like optimistic locking, where if there is lot of contention, then this will also not be a good performance. So it depends on your situation, that do you have lot of contention or not.
I agree, right? So because it is optimistic, right? So if it is always, because what's going to happen in the contention is exactly that thousand threads thing, right? Like, so there's a lot of ongoing transactions, that's trying to like kind of operate on similar critical sections, right? So then what's going to happen is, when one transaction kind of executes and and modifies a lot of these objects, all the other transactions are kind of going to fail, right? I think the book kind of talks about even an example in that scenario where, it's this is even more preferable where the transactions are short and small, right? Because if you have a long running transaction, where it's doing multiple updates, there is a probability that it's going to be in concurrent conflict with the multiple other transactions that are executing at that point of time. Yeah. So what you're saying is perfect. Yes, it has all the flaws of the optimistic approach where contention really kind of degrades the performance.
Okay. Yeah.
I think so finally it all falls down to two transactions executing snapshot isolation, but how do they actually figure out that the assumptions of serializability has been violated or not, right? And there are a couple of things, right? So either the issue could be with respect to stale reads, right? So I'm actually working on, because I'm working on a snapshot, right? So I'm kind of working on a snapshot. I basically read a value, right? But it's actually a stale value because even before I commit, someone else went and changed it, right? So that's not actually serial execution anymore, right? Now you actually have an interleaving if you try to look at the execution path, right? So that's one violation, right? So where you want to make sure that there are no stale reads that you have done as a transaction, right? And I think this example is pretty nice in terms of how the stale read happens and what we can do in order to prevent the stale read, right? So we have this 42 and 43, right? And then 42 is the first select on the on call the true and the shift ID for 1 2 3 4, right? And 42 also does an update, right? So it basically goes and modifies the on call to false, for a specific Alice. And now when 43 actually reads, right? So it's selects query, right? So the main thing with respect to here is 43 reads a particular value that is actually modified, right? So that has been modified, but it will not be able to see that update, right? Because it's using snapshot isolation, right? So 43 will not be able to see the result of this update. One, because first of all, the transaction itself was not committed, but even if it actually got committed, if 43 started earlier, right? So then this commit will not even be visible, right? So that is actually what they call in this particular as a missed write, right? So the fact that I'm trying to read something, right, which actually has a missed write, so the transaction manager notes it down. All right. So if you guys look at the third set of arrow marks, right? There is the first select query for 43. When that particular select query gets issued, right, the transaction manager makes note of the fact that there was a stale read over there, a possible stale read, right? And because of transaction 42, because of what 42 did in the update statement. So the transaction manager notes that down, right? So then, okay, fine. So let's say that executed, and then the update actually executed. The next statement is the update by 43. So as of now, there is no issue with the update. The update actually proceeds, right? And then 42 commits, right? So 42 commits, 42's commit will succeed, right? So because 42 doesn't actually have any stale reads associated with it, right? And then 43 commits, right? So in this particular, when 43 tries to commit, right, when it issues it, then the transaction, whenever there is a commit is whenever there's an ongoing commit, one of the first things the transaction manager tries to do is it sees whether any of the transactions that I've noted down for the currently executing transaction, right, any of the transactions that I've noted down as possible stale reads, have they committed or not? So that is the exact check that the transaction manager does. So in this case, it goes and tries to look at the list of transactions that I have to see, for 43 to succeed or not, right? And in that list, it will actually see transaction 42. And when it goes and checks the status of transaction 42, it sees the transaction 42 is committed, which means I should not proceed, right? So it aborts. If in this particular example, if the commit statement of that of 42 was actually the last one that gets executed, right? In that specific case, 43 actually would have succeeded. You guys get the main theme behind how to detect stale reads, right? So detecting stale reads is when I am reading itself, right? The transaction manager knows that that particular field has a potential stale value, right? It's still potential because we don't know whoever wrote to that particular value will either commit or abort. So there's a potential, right? So it notes down, okay, for the transaction 43, it notes down in a list of potential stale read transactions. It notes down the number 42 out there, right? And when 43 is trying to commit, it looks at this list and see whether any of the transactions, right, which could have given stale read for this guy actually committed or not. If even one of those committed, right, then you will abort this transaction. But if none of those are yet committed, then I'm fine, right? Then none of these potential stale reads actually turned into a stale read, right? Like not as of now, which means I can proceed and commit. You guys get that, right? I think the example is pretty spot on over here. So you just have to note down. So for every, whenever you, so this is on the read, right? Whenever you read, the update has already happened. So you know that it could be a potential stale read or not. You make a note of it. And when you commit, you make sure that none of the potential stale reads that you did are actually committed. And then you decide based on that. Right. So the next thing, so the exact same scenario, but what if the order was a little bit different, right? So in this case, what happened is both the first select query issue was issued by transaction 42, and the second select query was issued by transaction 43, right? Now let's say we only have implemented detecting stale reads, all right? And in that case, so far both read and both actually didn't detect any stale read, right? Because there is no update to that particular field yet, right? So now if we don't do this, whatever we are going to do in the following section, what's going to happen is it's going to actually allow the commit of both the transactions. You guys agree with me on that, right? Because it's going to, the first one is going to issue an update, right? Like so, and then when it's going to the next one is also going to issue an update, and then when the first one tries to commit, it's going to actually go and look at the fact that, you know, hey, did I do any stale rate? I didn't do any stale rate. I'm going to commit, so he's going to commit. And then when 43 tries to do the commit, right, he's also going to check whether he had any stale reads. There is no stale read, so he's going to commit, and it's going to be a success. The reason being, what's happening over here is here you're actually going to have something where the write happens later, essentially making the read that happened before stale, right? So this particular condition is the previous condition was the write happened before, and then you are trying to kind of match it up with the read that happens later, saying that read could be a stale, right? So here you already read it, but the write kind of happened later, right? In which case, when you write a particular field, all the values that read the field before this particular write, now they are also, which you call as a prior reads, right? So all those prior reads can actually be stale now. So that's what we have to guard against, right? And the way the book actually does it is so when transaction 42 and 43 reads, right, so you have to note down the fact that that particular record was read by 43 and 42. So when the first select executes, let's say there's an internal table one where it maintains, okay, fine. So for this particular record, index entry 1234, right? So it says that it was read by 42. And when 43 executes, which is the next select statement, it also notes down that fact that 43 also read this, right? So against that particular row, you have both 42 and 43 that have read this data. Now, the next thing is 42 writes to the database, right? So when 42 writes to the database, right? So then it basically looks to see whether for that particular row, which is actually on 1, 2, 3, 4, right? Have there been any other reads that have happened before? And it actually finds both 42 and 43 over there. So 43 is just me, but 43 is a different transaction, right? So it basically informs 43 at that point of time, right? Saying that 42 is now going to commit an update, or not commit, 42 is now going to do an update that might make whatever you have already read before a potential state read. Right? And 40 and 42, because it's the first one it does it, it actually issues that message to transaction 43. The transaction manager internally knows all these details, right? It's kind of issuing a message to transaction 43 saying, hey, be aware, 42 is something that you have to be wary about when you try to commit. All right. So in this, let's say there is an internal table too, where it maintains saying, okay, the list of transactions that I have to be aware of, right? So in that 43 will note down 42 over there. And then if we guys look at what the next statement is, the next statement is actually the next update statement done by transaction 43. Now, when 43 doesn't update, right, it again goes to row 1, 2, 3, 4, looks at the internal table, the one that we saw at the first line, right? So where it actually finds both 42 and 43 read it, right? So it knows that there is another transaction 42 that read it. So now it sends a message to 42 saying that, hey, you know what, hey, be wary of me, which is 43, right? Now, if you actually look at it, internal table 2 that it maintains, in 43, you'll actually have a list where 42 also gets added to there. So at the end of both these selects and both these updates, the state of this internal table 2, which like we can call it as a list of transactions that you have to be wary of, it will be exactly like this, right? Now which one is going to succeed, it depends on which one executes first, right? Let's say according to the specific picture, transaction 42 is the one that first executes, right? So transaction 42 executes, it goes and looks at its internal table 2, it finds 43 over there. Oh, I have to be aware of 43. It goes and see what's the status of 43. Status of 43 is still not yet committed, so it gets a green signal, it gets committed. So transaction 42 commits and it succeeds, right? Now when 43 tries to issue the commit, it again goes to this internal table 2. It actually checks, I mean, are there any transactions that I have to be aware of? It actually finds transaction 42 over there. It goes and sees the status of 42. 42 is already committed, because of which 43 decides to abort. And that's it, guys. So it's basically guarding against two different facts, right? You could pollute something before the read happens, or you could pollute something after the read happens. So the two different mechanisms that the book kind of describes helps us to deal with both these two different types of pollutions that could happen, right? With two different types of staleness that can happen. And like whenever a transaction so the question is, okay, hey, I'm trying to commit, make sure that nothing has changed from my snapshot isolation assumptions. That's all I'm trying to see, right? Like nobody has actually like done an update to any of the fields that I read, either before I read it or after I read it, doesn't matter, right? Uncommitted, of course. And as long as I maintain like the list of like potentially dangerous transactions that I have to check about, I'm actually fine. You guys get this, right? It's I think this is also kind of a little bit more straightforward, like the case one,
Yeah,
right?
but this implementation where we note down where what are the reads that are already changed. So this is not something we as an application developer has to handle. It's handled by, is
By
it
the
handled
transaction
already?
manager. Yeah, the transaction
Okay.
manager would do this. Yes, this is, yeah.
Okay.
Yeah, but
Because
there's one thing, right? I wanted to bring again that this is, you can tweak this based on how you want to do the escalations. There is a row level locking that you can do, or row level unlocking you can do, or table level locking you can do, or there's some even column level locking you can do. So
okay,
this is one level of isolation snapshot, that with the behavior for this is this, but if you want to do a different behavior, you can definitely do that, where both the transaction 42 and 43 can be successful even when both are committing at different times, if you do row level escalation. Because what you're updating, first one is Bob is equal to false for shift 1 to 3, and second one is Alice is equal to false for 1 to 3, right?
mm-hmm.
Both are two different transactions, two different at updates, right, for that doctor's table, right? So
Okay.
that being said, you can definitely, if you have a scenario, then you can look at the hints and you can actually set that flags in there based on your requirement and update it. This is general scenario where you have, when it does the snapshot isolation, and that's when this is the behavior for that. So for any question that comes, just say it depends on implementation is the best answer. And
I see. Yeah, I think, yeah. So what the book is trying to do is the book is trying to explain, one possible way in which this could
exactly.
be
So you
done.
should mention that, like whenever you're saying that general behavior, this is how it will work.
Okay,
But depending on our implementation, our usage or our needs, we can tweak it. But this is the general behavior.
perfect. Yeah,
Okay.
that's very true. That's very true, right? Yeah, it's concepts versus how it kind of and I think like Praveen kind of mentions, probably even on we can do this successfully even when there is no support for this. See, that's I think one thing I got from what Praveen said, right? So even when there is no support for a serializable snapshot isolation, or the maximum support is only for snapshot isolation, like using these hints and other kind of locks and stuff, we can establish consistency at the application level, right?
Yeah, because I worked on terabytes and petabytes of data and multiple day updates, and we did lots of tweaks like this. So,
Nice, nice, nice. Yeah,
so
I think you should definitely give us a session
Yeah.
one particular thing, right? Like
On
so,
locks and hints. Yeah.
yeah,
yeah,
yeah.
sure, definitely. I'll plan. This is long time back. Yeah.
Okay, nice. Okay, guys, I think that kind of essentially, yeah. So the one last thing probably, okay, so we said snapshot isolation gives good performance because writers don't block readers and readers don't block writers, and that kind of terminology even applies over here because we kind of allow to proceed them with just the fact that like if it violates serializability, we have to avoid them, right? So that's always there, and yeah, I didn't finish the summary part of it. So basically, the to just summarize this all things, right? We saw dirty writes, we saw dirty reads, and then we saw that read committed can be used to fix them. We still saw read skews, and which is basically non-repeatable read. So how to make it repeatable? Read from a snapshot. So snapshot isolation comes into picture out there. How do you implement snapshot isolation? Use multiple version controls, and using clever algorithms to that knows what my when I start the transaction, what my ID is. It knows exactly what got committed before me, so it uses those versions. And then so all these have been dealing a lot about reads. So there are also a couple of write related issues in addition to the dirty writes that we saw at the first stage. The first one is lost writes, and lost writes has to handled using atomic writes or law or explicit locks or even cache operations, or even database could help with that. And then we also have write skews, which are basically the phantoms. We discussed the phantoms in quite a bit of length. So the primary idea of solving the phantoms is try to use a lock on the select query. So that's where we started seeing about index range locks and predicate locks. So all these are weak isolation levels. Then we started seeing about serializability, three different ways. Read your writes, sorry, not read your writes. I'm just confused. So that's basically replication lag issue. Sorry. So it's the three different ways. One is actual serial execution, and then two-phase locks, and then you can use predicate locks on top of the two-phase locks or index range locks. And then we finally saw serializable snapshot isolations. We kind of saw two different ways that we can implement SSI on top of serializable on top of snapshot isolation. One is how do you detect stale reads, and how do you detect these stale writes, right, on values that were already read before, right? So we saw how to handle them. Like just have a list of transactions that are potentially dangerous to you, and when I want to commit, see that none of those dangerous ones actually got committed, and then you should be able to abort or proceed based on that. And that essentially I think covers the transactions chapter. um, Hopefully you guys had a nice time. I think it's one of the deeper chapters in the book, I believe, right? So there is one more that's even more deeper than this. That's the consensus one, but I think until now this is probably the deepest chapter we have seen.
So I just put a link in there. You can actually save that. That has all that versioning. How the lock escalation works at table level, row level, and how it gives a detail that you can discuss at least 3-4 sessions just for lock
Just using
escalation.
this, is it? Okay.
Also, it depends on updates. It's different versus deletes is different versus selects is different. So there's different escalation procedures and protocols that it takes.
Okay.
The last one, if you can see it, it's so elaborate. Instead of just range, and it will take you into much. If you're interested in this, right? It's where it will go into much more detail with log granularity and read committed, snapshot, read uncommitted, repeatable read, snapshot, serializable with different scenarios. The documentation is really, really good and with examples.
I see. Amazing. Yeah, I think we'll definitely have a separate we'll pull you in, Praveen, for a separate session on some of these
And
concepts.
this is applicable to all Azure database. Anything Microsoft related, this is applicable. And this should be the best practices that other database also trying to do, but Oracle is always uh, little bit different from Microsoft. And me coming from Microsoft, I have little bit more knowledge about Microsoft database than others.
Nice, nice. All right, folks. I think we are also running into the next meeting, I believe. So thanks, everyone. So let me let me stop sharing, and let me also stop recording. Right. So